This is a supplementary of the paper sampling with Riemannian manifold Hamiltonian Monte Carlo in a constrained space submitted to ICRA 2025. As shown on the left, standard RMHMC generates samples that deviate from the constraint manifold, resulting in violations of equality constraints and inaccuracies near boundaries. In contrast, our proposed CRHMC, which is shown on the right, produces samples that strictly remain on the constrained surface without such corrections. This diagram summarizes the overall pipeline of our constrained sampling framework. Starting from a user-defined constrained space, we first incorporate inequality constraints using a log barrier potential, which shapes the Riemannian metric. As shown on the left, the geometry of the metric naturally guides the trajectory toward the valid constrained manifold. Then we visualize how samples generated under this metric remain tightly near the constrained surface, without violating the boundary. Here, we compare sampling results between a standard metric and our proposed constraint-aware Riemannian metric. Using the standard metric, samples are scattered near the constraint surface but frequently deviate from it. In contrast, our proposed Riemannian metric shown on the right ensures that all samples lie precisely on the constrained manifold. Next, we focus on how our method handles equality constraints. We use a null space projection to remove directions that violate the equality constraint. To achieve this, we introduce a Lagrange multiplier that explicitly enforces the equality constraint during integration. Without the Lagrange term, the system suffers from numerical drift and samples gradually deviate from the constraint surface. As shown on the right, by adding the Lagrange term to the Hamiltonian dynamics, we explicitly enforce the equality constraint throughout the integration process. Finally, we integrate all components including both equality and inequality constraints and simulate the full constrained Hamiltonian dynamics. In the following experiment, we validate whether the generated samples indeed remain on the constrained manifold as intended. In this experiment, we define a constrained space with both a linear equality constraint and an inequality constraint represented by a circular obstacle. Our proposed CRHMC method successfully generates samples that lie exactly on the constraint line while avoiding the obstacle. The first plot confirms that the equality constraint is satisfied throughout the trajectory, with deviations on the order of 10 times 10 to the power of -7 indicating near machine precision. The second plot shows the value of the inequality barrier, verifying that all samples remain outside the obstacle region while maintaining a safe distance from its boundary. To summarize, we proposed a sampling framework that directly embeds both equality and inequality constraints into the geometry. In the future, we aim to integrate CRHMC into control tasks such as MPPI and motion planning under constraints. Thank you for watching. If you have any questions or feedback, feel free to reach out to us.